Alright, welcome to Module 2. Before we get started with this, go watch the videos on the Colbert Report that are in this module, because they're fantastic, and we're going to be using them as examples for the rest of this lecture. So, if you haven't already, stop this, go watch those, then come back. If you have, let's move on. So, Excelmageddon, the terrors of Excel, and Rogoff and Reinhardt's paper. This was fairly recent when this happened. This came out in May, I want to say, and has caused quite a stir because, as Colbert talked about, this paper has been the basis of a lot of policy, a lot of decision that's affected a lot of people's lives, and to find out that it's wrong has really shaken a lot of people and made them very upset. So, I want to look at two things, what they did wrong and what they did right. So, what did they do wrong? First, they used Excel. Now, I know last week we talked about how great Excel is and how it's used for a ton of different things, and that's true. Excel is amazing, but it has its limitations. And when you get into doing some complicated analysis, some data modeling, or any sort of advanced statistics, Excel really can't quite cut it. And so you need to move away from Excel depending on the sort of analysis that you're trying to do. And Rogoff and Reinhardt probably should not have been using Excel. And the reasons for this are primarily because, well, one, when you're doing advanced statistics, Excel doesn't do it right. Something about the way they've coded it gives it incorrect answers. And the other reason, which is oftentimes even more important, is it's very hard to document what you've done in Excel. It's hard to say, okay, this is what this formula means, and then this is what this formula means. Because as you experience with the first assignment, you can hit equals and you can type in a little bit of code. And a lot of times that code, you're doing something really simple, like getting an average or getting a median, maybe summing some data. But you can make formulas really, really complex where you've got if statements, so there's some logic. So if a number is greater than 2, then give it this number. If it's not, well then, if it's less than 3, then put 5 here. And you can just make these really, really complex statements that get very hard to, it's very hard for someone else to come in and understand them. What's also interesting about Excel is, while you were just selecting a couple little groups of data, you can group data across multiple worksheets, across multiple kind of their individual spreadsheets, but they can all reference each other. And it gets really, really hard, really fast to tell what's going on. I was working on a project a couple of years ago where we were trying to project where people were going to live in the state of Utah in very, very small areas. So within cities, where people were going to live, how much they were going to grow. And someone else had done some work, and I asked for their spreadsheet, and I looked at it, and I spent about 2 days just staring at it, going through the formulas, trying to figure out what was going on and why they had done what they had done. And in the end, I'm like, this is way too complicated, and I cannot figure out what is going on, so I just redid it all. It was a waste of effort, and it was because it was a very complicated spreadsheet, and there was no way for me to know what was actually going on. So that is probably, I would say one of the biggest problems with Excel, is you just can't tell what's going on. And so when you move to a programming language like R, there are other ones like Stata or SPSS. You can do it in general purpose programming languages like JavaScript or C. You can actually write in comments and explain what's going on. So it makes it a whole lot better. The other thing they did that really skewed their results, like Herndon pointed out, is they biased their sample. They left out some countries that are kind of important countries: Canada, New Zealand, and Australia. Now, sampling is one of these important things that we get into in sociology and when playing with data, because it goes into how you're actually getting the data. And there are two ways that people can go about getting data. you can take a census, which is where you talk to absolutely everyone. We try and do this in the United States every 10 years. It's mandated by the Constitution that a census is taken where we count the number of people in the United States. And the count is supposed to be absolutely everyone. And if you can get absolutely everybody, then it's a census. The problem with censuses are they're incredibly expensive, both in terms of time and in terms of money. And so censuses aren't really done very often. I mean, they're great because they provide the most rich data set possible. So if you were trying to sell a product, or if you were trying, let's not do products, let's not do marketing, although marketing and sociology really go hand in hand. Let's say you were trying to look at educational attainment by race. And, well, just if you were doing a census, you wouldn't even have to worry about race. You'd just say, I want to look at how much schooling everybody's had. And then you go talk to absolutely everybody and figure out how much schooling everybody had. And then you could do some simple averages and say, okay, these people, or proportions, and say this group of people usually gets more education. They go to school longer than this group of people. And if you had a census, you'd have everybody and it'd be fine. But it would take a really long time. And even when we do the census in the United States for the government every 10 years, we don't actually get everybody. Not everybody gets counted. Some people aren't home, some people moved away, some people just refuse to answer the questions. So it's really close. They get really good, but they don't get everybody. And so instead what we use, usually, when you're not the US government and have tons of money to use for this sort of thing, is you try and get a sample. You get a group of people that represent the total population of whatever you're studying. And while it's not always cheap, it usually is a lot cheaper than a full census. And what we found is that when you take a sample, if you do it right, then you can actually approximate, you can get close to the actual total population in terms of what's going on. And so instead of, if you're looking at how much schooling everybody has, instead of looking at everybody, what you can do is randomly select a bunch of people. If we wanted to just look at educational attainment, the years of schooling just in Salt Lake City, we could talk to everybody in Salt Lake City, have a census, or we could grab a phone book and pick every fifth person and call them up, talk to them, and say, how much schooling did you get? And that's a fairly random way of getting people. Every fifth person in the phone book. And it would be pretty good. And there's a whole bunch of different ways that you can try and get samples. So I just talked about a random sample, which is usually the best way. It's the most representative of the population, if it's truly random. But again, as with most data collection, if it's going to be really good data set, it's also really hard to get. And getting a random set of the population is really difficult, because to truly make it random, you would need a list of every person in the area that you were trying to talk to. Every person in the population, and then you randomly select them. So if you think for a minute, I just said, if you grab a phone book and grab every fifth person, that would be a very random population. But it's not really representative of the total population. How many of your phone numbers are in a phone book? Actually, how many of you have even seen a phone book? Phone books are dying. And it used to be, this is exactly what people would do. People used to actually take phone books and look through them, but that was really before cell phones, when everybody had a landline, and everybody was listed in the phone book, pretty much. Almost everybody was listed. Now with cell phones and do not call lists and other sorts of things, you're going to bias your sample. You're going to exclude a certain group of people. And so that's really not a good way of doing it. You're not actually getting a true random sample where every person has an equal chance of being brought into the sample. And so random's really hard. A slightly easier way to do it is a stratified random sample. Stratified means that we're actually breaking it into groups and looking at the proportion of the groups in the population and picking a sample based out on them. So if we know in the general population of Salt Lake City, where we're trying to figure out how much schooling everybody has, we know there's a difference. We know that there are more women than men in Salt Lake City. I don't know if that's actually true, but we'll say it is. Say there's 60% of the population are women, and 40% of the population are men. If that's the case, if we know that the population is not equally distributed between these two groups, we could stratify our sample and say that, okay, out of the 3 million people that live in Salt Lake City, we know that 60% of them are female, and so out of our 3 million, we're going to interview 300 people. And out of that 300, we're going to make sure that 60% of them are women and 40% of them are men. We're going to break down our sample so we know that as far as gender goes, we have an equal representation of women and men. So that's another way you can do samples. Again, you're trying to be random, you want to get the whole population, but it's hard, and this is one way that you can make it a little bit easier by breaking it down that way. But still, you need a pretty good list of who's going out, of who you're using. A systematic sampling is not quite random. Out of your list that you have, you just kind of, you make some sort of rule of who you're going to get or what qualifications they're going to have, and then use them as examples, as representatives for the rest of the population. A snowball sample is another way you can do it, where you go talk to someone. This is how chain letters often work, is you go talk to someone and then say, okay, give me the names of 5 friends. And then you go talk to them, and you ask those 5 friends, give me the name of 5 friends, and you go talk to them. And so it snowballs. You get a bigger and bigger sample, but not everyone is equally likely to get into your sample and represent the rest of the population. It all depends on who you start with. And there are a whole bunch of other sampling techniques, and you can take whole courses on different ways to sample populations. But the point is to try and get a representation of the larger population. And this is where Herndon did it right. This is where Rogoff and Reinhardt made a mistake, because, and I don't know if they were using a sample of countries or if they were using a census of countries, if they were using every country. But due to whatever reason, they left out some really important countries, and that dramatically changed their results. And this is a problem. And yeah, anyway, big problem, big issues. Right, the central limit theorem. The reason why sampling works is because we found, and there's a whole bunch of math behind this, and the central limit theorem is a math theorem, that the bigger your sample is, the more accurate it's going to be. That's really the basics of the central limit theorem. And so whenever you're doing a sample, whenever you're trying to get some data from someone, collecting your own, you want to have as big a sample as possible. Get as close to the census as you can. And there are ways to kind of figure out what the minimum number of people you need in a sample to represent a population are. Or is. Anyway, but we're not going to go into that. If you're interested in that, there are classes, and talk to me, email me, and I'll point you in the right direction of where you can get those. But there are very, very good ways of getting a good sample to represent the population. And in sociology, this is really what we want to do. We want to look at a few people, as few people as possible, to represent as many people as possible. To say, this is in general how things work. This is in general where the differences are, or why. Okay, so let's look at what Rogoff and Reinhardt did right. First thing they did right is they told a good story. You can tell it was a really good story because so many people listened to it, and they actually made decisions based on it. They also had good hypotheses, and they used measures of central tendency. Same things we talked about last week: means, averages, and all these things are good. It's just how you become effective using your data. And I know in the introduction, if you watch that, the course mechanics, or introduction, whatever one it was, video, I said, this week we're going to look at measuring difference. And I was thinking this would be great. We're going to talk about the Gini coefficient and Thiel's coefficient, look at chi-square tests of independence. And then I was listening to another lecture, and going back and looking at these Colbert Report things, and they said really the vast majority of what you're going to be doing is, of most data analysis, are not these. They're really simple. They're proportions, they're absolutes, they're means, they're averages. These numbers, these things, when you talk about a mean or you talk about the absolute difference, the change that occurs, or the proportion of change and representation of something else, these are the numbers that are easy for people to grasp. These are the numbers that tell a good story. And so it's easier, and you've already done that, and so we're not going to do the Thiel's coefficient and the Gini coefficient, which are great, they're wonderful, but they require more math, and oftentimes these are just fine. And so the last thing I want to talk about is this picture, this graph. This is called a histogram, and it represents measures of central tendency. It represents the mean. And so what you see here is each one of these bars represents a group of data. And in the title it says histogram of R norm 1000, 0. And this is a piece of code that says randomly generate 1,000 pieces of data, 1,000 data points with a mean of 0. And so if you look down at the bottom of the graph, 0 is right in the middle. This has a mean of 0. And as you go away from 0, in either direction, towards -3 or +3, you see there are fewer and fewer observations. The y-axis is the number of observations that fall within that range. And so the tallest bar is roughly, the tallest bar goes from 0 to about 0.5 as far as the range. And then the y-axis, the height of the bar, is how many of these 1,000 observations are within that range of 0 to 0.5. It's about 200. And then from 0 to -0.5, it's a little bit less, about 180. And then you keep going down. This is what's known as the normal distribution. And this is something that is found throughout nature. That the vast majority of most phenomena kind of fall in this pattern, where there are really few small numbers and really few really large numbers, and everything's kind of in the middle. And this is what measures of central tendency, the mean, the median, and the mode, are really looking at. So when you say the mean height of an American male is, 5'9", what you're saying is, 5'9" is that middle point. And the vast majority of people, up to 60-70% of the population, are within 3 or 4 bars of that. And one of the ways we measure those is called standard deviations, but we're not going to look at that right now. And so this normal distribution, it's also called a bell curve, is something that is foundational in statistics. And for good reason. Because this is what helps you tell the story. This histogram is a way of looking at it, but when you create the mean number of population for the states, if you made a graph, if you made a histogram, it would look probably something like this, where a whole bunch of states have roughly the same sort of population. And then you've got some states with a really low population, like Wyoming and North Dakota, and states with a really, really high population, like California. But most states are kind of in the middle. And so when you're talking about, when you say, here's the mean, here's the average, you're saying this is kind of where most states are. It's not exactly, there might not be any state that has exactly this number of people in it, but most of them are right around here. And then we can compare them. And we can say, well, how different is our state from kind of the mean, from the average? And this is what we do. Even when we start doing more advanced statistical analysis, when we start looking at regressions, we're still kind of dealing with means. We'll get some numbers that says, there's this much influence of, let's see, what's a good example? We'll do age and height. You can say on average, the older you are, the taller you are. You're still looking at an average. You're still using kind of this middle thing, and you say, well, this is only an average. There are a lot of people who are taller, and there are a lot of people who are shorter. And as you grow up, there are going to be taller and shorter people, but on average, here's how much the difference is. Here's how much association there is between age and height. Hopefully that makes sense. But this histogram is something that you'll be making in your assignment. Not this exact one, although I do show you how to do it, so you can play with it if you want. And it's fun to do it with random data like I did using this rnorm command, because there's a whole bunch of different, you can watch and see how it changes. Because this is just randomly generated 1,000 observations, all with a mean of 0. And if you do this command, run this over and over and over again, you'll see the numbers shift all over the place. But it will still have kind of the same distribution with a whole bunch of, with the majority of the data points right in the middle. But it might go out to, on this x-axis at the bottom, it could go to -20 and +20, but still the most units are going to be right around 0. Or it could only go from 0 to -0.5 and +0.5. You'll still have most of them right in the middle. And there's all sorts of different ways to get to randomly generate 1,000 observations with a mean of 0. This is one. So sorry, that's kind of fun if you want to play with that. You have not understand, this is a histogram, and it's different than a bar chart because the width of each bar is very specific. It actually has a number. A bar chart doesn't always do that. And so you can group a whole bunch of data in bar charts and manipulate the way it's presented that way. And I'll show you how to do that later. But histograms are nice because they do accurately represent the data. These ones are all of an equal width, so you know that there's an equal number, an equal range for each of them, for each bar. And I think that's all for this. Oh, wait, hypotheses. Sorry, not all for this. This was the other thing that Rogoff and Reinhardt did right. They had hypotheses. And when you do science, hypotheses are really good because they force you to actually think about how things are going to be put together. And their hypothesis was that countries with high levels of debt, depending on their GDP, so they normalize it just like you guys did. You normalize the data by dividing it by the dividing the growth by the total population, by the initial population. What they were doing is they normalized the growth by, or they normalized the debt, the amount of debt, by the total GDP, or gross domestic product, how productive we were. They expected something to be different, and they tested to see whether or not it was. And there's some specific terminology when dealing with hypotheses. And the first one is the null hypothesis, usually referred to as H0 or H0. And the null hypothesis is always the same. It's that there is no difference at all between two things. So whether you're looking at difference in population between states, or economic growth based on debt, or educational attainment based on race, or anything, differences in pay by gender, the null hypothesis is always there is no difference between these two groups. And then there's your actual hypothesis, which is H1. And you can have multiple hypotheses, H2, H3, H0, H whatever. And that's always that there is a difference. And using HO and H1 kind of forces you, and writing these out forces you to think, okay, what difference do I actually think that there's going to be? Do I think it's going to be greater than? So do I think women are going to have greater salaries than men? Because you'll probably find that that's not true. If you say, well, no, I think men will have greater salaries than women, well, then yes, that is true. But either one of those, you can have either one of those as H1, and one might be true and one might be false, but either one of them will prove H0 false, so there is no difference. And so this is just a bit of terminology that's kind of important that you'll see a lot when you read papers. of these H1s and H2s. These are hypotheses, and the rejection of the null hypothesis. So the null hypothesis is just that there is no difference.